today we have Maximilian Rimbach-Russ giving the presentation. Onto the presentation. So we have Maximilian, who is a group leader here at QuTech. Max received his PhD in University of Constance in 2019, and then he was a postdoc at QuTech from 2019 to 2021. Then he was awarded a Venny Talent Fellowship from NWO. And then he became a group leader in 2023. He got a VD grant and is currently leading the semiconductor qubit modeling group, focusing on qubits and modeling qubits. And today he will talk about control of baseband spin qubits.
Thank you very much for the nice introduction. Yes, so I'm from the group here, a group leader here at QuTech, and these are actually the people who do the actual work. I'm just sitting behind my desk and managing all the stuff. No, today I'm actually showing stuff where also I myself are involved, which was already published and from the last year. So maybe go back in time. Let's go back to 1995. Who knows this paper here? Maybe some hands up. So I saw 3, 4, 5 hands. Okay. Yes, I know David is online. So just for David, there were 5 people in the audience who know this paper. If you go on Wikipedia, these are actually David DiVincenzo's criteria to build a quantum computer. And now just make the probe again. Who knows the 5 David DiVincenzo criteria? Okay, now everyone except a few people who might just coming in are raising their hands. Okay, these criteria are out there for many, many years now. And I think the community has done a fantastic job at building a quantum processor and fulfilling all these criteria. So maybe asking you again, we don't have a fully working quantum computer who does practical applications yet. So which of the criteria will still need most of the attention to? Yeah, I heard the word scaling here. Yeah. So the first one. So we have everything except a scalable or a truly scalable system yet for quantum computing. There are many platforms, so we have the choice which platform we can pick from, and we have many degrees of freedom where we can actually encode the information into it. And here are a few examples. And here on the side, you see the most advanced free ones. And then here also semiconductor qubits, because this is what I'm talking about. So if I draw a qubit, who would draw a qubit as a very instructional point in this way? Half people. Who draw it this way? What's the difference, you might see? Okay, nobody, that's okay. Who draws it this way? 1, 2, 3, 4. Okay, I know from which field you're coming from. Yes. So most people actually draw a qubit where they have a ground state, which is 0, and the excited state equal 1. And then for a qubit to actually work, you need several properties. They're all actually part or described in the DiVincenzo criteria. But for most of it, you need to operate with your qubit, you need to initialize, and you need to measure it. Operations are one part. These are classical. You can think of flipping this, the qubit state. This is the classical part. But we all know that you can also stop in between if you do a unitary rotation, and then you do quantum gates, and these can be in the X and the Y direction. So if you look into the very rich field of quantum computing. Most of the qubits are operated by oscillating fields. You just apply an oscillating signal, which brings your state slowly from one state to the other state. These are called Rabi oscillations, and these are very old, even before quantum computing became a thing. They're in NMR, very important. If you draw it in the lab frame on a sphere, what you see are these really nice oscillations around. So in the lab frame, your qubit is always processing with the energy frequency. Basically, it's never standing still, but since it's a phase, you can compensate for. This means if you go into a rotating frame, this is what we are doing. We know the resonance frequency of the qubit. We go into the rotating frame, and then we have these wonderful oscillations here around. However, that's in a rotating frame. And if you're off resonant, so basically if you don't hit the resonance frequency, then you're just doing these tiny little rotations here on the top. You're off resonant, you have a large detuning, you're not hitting, all the other parts is averaging out. And the same thing happens if you go into the rotating frame, because you still have something very fast rotating in the rotating frame. If you're not on resonance, you get a very similar picture depending on the choice you pick. So essentially, your qubit is a very good filter. It is very sensitive to one frequency and insensitive to all other frequencies. This gives it really nice properties, making it robust against a lot of noise, except at the qubit frequency most times. So coming back to the question, which qubit to pick. And in this talk, I talk about using a physical electron system in condensed matter and using the spin degree. And very important to note in this talk, electrons in semiconductors, you can either use actually an addition of an electron in a filled band, just adding one more, or you can also take one out, and this gives you an effective whole part. And this is how they look today. This is a picture of Intel. I made a very fair comparison, very old devices from other groups and the very fancy new ones from the semiconductor. The reason is I couldn't find all the fancy pictures because mostly they're behind companies and don't reveal all the details. However, there are many open problems, and we talked about scalability. So if you're coming back to the questions, in order to have practical quantum computer, we need a lot of qubits because we need a lot of qubits to actually do our computations. And then we need even more qubits because error correction needs also be performed. So we have an overhead. And this redundancy we can actually use to make a very high fidelity, even if our physical operations are not near perfect fidelity. The numbers is debatable. The exact numbers estimates range from 100K for Schwar's algorithm up to millions for more quantum chemistry simulations. So if I look on this semiconductor, these are 108 quantum dots, which all of them can serve as a single qubit if you use a single electron spin. And the size of this is only 3 micrometer. So it's a very, very, very densely packed qubit. And this is an old vision from Menno Veldhorst and UNSW, where he was still at UNSW, how to build a quantum computer based on such qubits. You can see it's very packed and very dense and very optimistic in terms. And people have done some rough estimations. If you need one control line for a fast signal. Let's say doing your oscillations. You typically have wires just going out of your fridge for 1 million qubits, which are the size of, depending on a few tenths of centimeters in diameter, even to a meter, depending on which wires you pick. So you have a really big problem there. And therefore, there are a few open challenges, which are especially for densely or small qubit systems. The first one is clear wiring, the wiring issue, how to actually bring the signals to all your qubits such they can be operated. And then there are more problems which become more important also once you scale up. Crosstalk, and crosstalk is not only the signals itself with crosstalking, but there's also quantum crosstalk. So you need an interaction which you can turn off. And especially for spin qubits, qubit variability is one of the bigger issues, because all your qubits are slightly different because the condensed matter, the semiconductor itself, has impurities which slightly change the properties, giving rise to different qubit frequencies. So how, if we really go back again in time and look at the original proposal for spin qubits, we actually see a very creative way how the two authors, Daniel Loss and David Chenzo, envisioned to build their qubit. And one way, one part we use still nowadays, but the other part we might actually use again. So if I guide you through this picture, what you see here are two electrons, E1 and E2. They serve as the qubit. And then you have here close by ferromagnetic dots. And these ferromagnetic dots, these ferromagnetic dots here, they can actually cause slight changes in the quantization axis of the electron. And this way you can actually get a tilt in your spin because you have something ferromagnetic with a magnetization close by. And then if you slightly hybridize your wave function with this dot, you get a tilt if it's originally in the opposite direction. The 2-qubit is actually even more easier, because for the 2-qubit interaction, you just have to bring them together and bring them apart. Because of the Pauli principle, you always get a exchange energy penalty, and this gives you a direct access to a 2-qubit gate. And very important, this original proposal, and I spoiled already the punchline, didn't talk about oscillatory oscillations at all. So there's no mentioning that you should actually use Rabi frequencies to operate the qubits. Here again, the 2-qubit interaction a bit closer. The idea is you just take your two electron wave functions in your quantum dot, and you start to make them overlapping. There are different ways to make them overlapping. You can imagine. One is to bring them closer. One is to raise or lower the barrier, meaning the wave function spreads more. Or the third one is also to tune them. The tuning was actually the easiest and which was used in the beginning. However, it's also the most noisy version of it. And then people start to do it symmetrically by lowering and rising the barrier. But nowadays, actually the moving together and moving away is becoming a very appealing method, because it allows you for mobile qubits, and then they just interact, and then you have a really strong turn-off value. And the interaction here is directly given by two physical interactions, the Hamiltonian itself, it's the exchange interaction, and the Zeeman interaction. In qubit language or quantum computing language, the interaction is given by a Heisenberg type of interaction, which is XX plus YY plus ZZ interactions. Oh, this should be a plus. There is a typo in the formula, so it's actually the h bar omega. You have a single qubit frequency, which comes from the G factor from the Zeeman interaction. If you assume both G tensors to be G factors to be identical, you get a equal splitting here. And if you have such interactions, what you do are so-called swap oscillations, not to confuse with I-swap. These are swap oscillations, which is a classical oscillation, but if you stop at half point, you get actually a square root of swap, and this is a maximal entangling gate. And this is how you control the 2-qubit interaction. And then people thought, okay, we have this magnetic field dependence. It is very well known from NMR. Magnetic fields are slow and global. So it's very hard to really confine them to the small size of a quantum dot. So people came up with a second way to think of a qubit. And instead of using one spin, they actually used multiple spins. And it can be shown that you need at least 3 spins to do that, to get actually a qubit where you don't need the magnetic field at all. The magnetic field, just throw it away. You only need the exchange interaction. And then you get an all electrically controlled spin qubit, a spin qubit using 3 spins and the subspace part of that, which is shown here. So you have 2 exchange interactions. They're called JZ between the first and the second, and JN between the second and the third. And this is sufficient to give you rotations. Or they are not orthogonal, but okay, use just multiple of them to actually get arbitrary single qubit control. The real benefit is, if you think of it on scaling, why to do this? Because unlike the magnetic fields, there's no energy gap actually in the idle state. This means if you turn on one of the exchange interaction, you immediately do your gate, and you just need to turn off. And you don't need to do anything else. You don't need to match frequencies. You don't need to be very precise in the timing. The only thing what you need to be very precise is that the integral, meaning the times or the area of your pulse in the exchange interaction, actually is the gate you want to perform. And this can be, and then you can interplay between actually time accuracy and voltage accuracy, and actually can really tailor it to the need of your electronics. And this is how here in the newer version where they showed a working 2-qubit cell of exchange-only qubits, meaning 6 spins. And what you see here is they just add pulses, like you think how to control a transistor, just a pulse, which fits the area, and then they get their quantum gates. So good. We already have a baseband qubit, so what's the issue? Shall I stop now? It's really nice. No oscillatory signals needed, so you only have baseband control, something which you can easily multiplex compared to other signals, which is not so difficult in crosstalk because you have wide band pulses. And in the end, you can think of it as a digital way. You have one pulse or multiple pulses, which you just call it the digital 0 or 1, do it that pulse or not. And then what you get out is a gate. Of course, there's no free lunch. And the problem comes if you look at how the qubit is actually encoded. And to make it short, it's complex. We use a subsystem, so if you have 3 spins or 3 qubits, you have an 8-dimensional Hilbert space, but you only pick 2 states out of it. Essentially, you can pick 4 of them, and then you get a kind of a double version of a qubit, where 1 degree of freedom is a gauge degree of freedom, and you can just ignore it. So your qubit always works in both. But this gives some complications. And these complications is you have close leakage states where your information can leak into. And with leak, I mean information which goes outside of your computational state into states which you cannot detect and measure. This is especially problematic for quantum error correction. So this always needs to be compensated and gives you additional overhead. And the second is, because of this leakage, you actually have quite complex fault sequences to actually do the gates. Already talked about that the single qubit gates already became more complicated. Okay, but that's only 3 pulses or 4, depending how you count. I would say that's okay, because they can be very fast. But for the 2 qubit gates, you have to use between 11 and 50 pulses. And if I see the audiences already a bit skeptical, the nice thing is the gate time is similar to what you would do a normal 2 qubit gate if you just do a single in other versions. However, having this precise control is quite demanding also on the control electronics. So the question is, can we find something better? And new. Let's go back, take inspiration from the original work with no oscillatory signal. So somehow they already knew how to do a 2 qubit or a single qubit gate without the need of these. And exactly what they did is they tried to hybridize their spin with doing hybridization with a close by ferromagnetic dot. And then they also have the second part here on the bottom, which they mostly used actually for the readout, but they actually tunnel between these 2 dots. And then you can think, okay, if I have 2 quantum dots which have a slightly tilted Larmor vector, if I tunnel just very fast between them, I can do qubit operations. And this is exactly done here. So you can think here of this pulse sequence is you have 1 dot which has a certain quantization axis and a tilted second dot, and you tunnel just between your first and your second back and forth. In this way, when you go from the first, you actually freeze your state. In the second quantum dot, your qubit still remains and your state remains. However, because now the energy is not parallel to that axis anymore, but tilted, you actually get the oscillation. And then if you time it correctly and jump back, you actually can do operations with them, and actually very efficient ones, very fast. So tunneling and on. So you can now actually do operations which are more or less on the order of the Zeeman splitting and not the Rabi frequency, which is typically much smaller between them. And there are 2 experiments already shown that. The first one is using holes, which I come later into it. But here you can electrically more or less control the quantization axis. You hop in between. And in this experiment, it was just as shown. You just jump back and forth, and they actually have done it for 2. So basically for 4 dots, so basically for 2 qubits simultaneously. And the second experiment was done in the group by Lieven van der Sijpen using silicon, and you have actually a spatially dependent magnetic field. You have nanomagnets which can actually create a very strong gradient. So if you go on one side or on the other side, you just experience a different magnetic field. And essentially, it's the same from a qubit point of view. You just jump between 2 positions where you have a different quantization axis. However, would you call that scalable? And I came up here with some arbitrary requirements for a scalable electronics. One is short pulse sequences, okay? You don't want very, very long sequences to actually operate a single qubit, because then you can just do rubbies again. Baseband signals, because they're easier. You don't need local oscillator frequencies with high frequencies. So you ideally need less fast lines into your fridge, or even make these signals, create them in the low temperature. And then you want something which is, I would say, you can call it a clock. A clock is how you need to know what information do you need to know about the current status of your qubit. If you have a qubit which is defined in a rotating frame, you need to know very precisely at which time you are. And this typically be done by using your local oscillator and attaching everything with it. And your local oscillator actually counts the time. But now imagine if you have tens, millions of these qubits, and all of them have different frequencies. They become very easily very crowded to actually measure all the frequencies. And having a low frequency, a clock or a slow clock, actually helps to distribute the signals by synchronizing, because then the exact timing doesn't depend on picoseconds, but maybe only on nanoseconds or even more relaxed. So this gives some kind of ease for multiplexing and actually also building them. If we look on hopping spins, we have the first short pulse sequence, definitely a green. Baseband signals, I would say true, but they need to be sharp. The tunneling needs to be fast. This can be adjusted, but there are also requirements. You cannot be too fast, because then you excite other states. So I would say it's good, but it can be better. And the low frequency clock, no, for hopping spins, you need very precise timings. And if you're still skeptical, please have a look into these two papers. It's explained there what are the requirements. So if we go back and look at the exchange-only version, where we just have signals coming in, which we can call even digital, like one bloop or kind of a collection of pulses, which does give us directly one gate, and it can be slightly delayed and doesn't matter. Because in the baseline, the qubit frequency is actually, the idling frequency is actually 0. So if we look from a theory point and try to reverse engineering all these properties, what we want, we actually want to have a qubit Hamiltonian, which looks this simple. You have a sigma x component, basically one axis, which you can control by using voltages, and you have a y axis control, which you can control by voltages. That's it. You don't want more. And very important is that you can actually turn these terms off and on arbitrarily. Because if you turn them off individually, the Hamiltonian commutes, and there's no very sensitive time, there's no time sensitivity required. And ideally, you also don't want here a 0 set. So you don't want in the idle that your qubit is actually evolving in time. And this is in the lab frame and not in the rotating frame. So how can we construct such a Hamiltonian? We look into condensed matters, of course. And in condensed matter, the magnetic field interacts with a spin using with the so-called G-tensor. In most materials, especially in electron-like materials, the G-tensor itself is only a factor and a diagonal with identity matrix. But in some materials, especially with some spin-orbit interactions and holes present, this G-tensor is a matrix which has several components. And you can actually write it as a 3x3 matrix with 9 components. And now we want that all of these 9 components can be actually controlled by voltages. And if we can actually create a G-tensor where we have a form where we can separate in plane, also X and Y direction blocks, from an out of plane Z block, so having here effectively 0 here on the sides, we immediately get back our Hamiltonian we're actually looking for. If we also can control arbitrarily these in-plane blocks. Jumping into the material where this is possible, germanium qubits are becoming quite advanced. And a germanium qubit, you can think of it, you have a 2-dimensional hole gas, which is sandwiched between a buffer material on the top, and it can have a substrate below. And if you look at the relevant bands for Hall qubits, you will see that there are actually 4 bands relevant, and these 4 bands, they are the 2 heavy Hall bands and the 2 light Hall bands. But because we are talking about holes, let's flip everything around, because holes like to do exactly the opposite like electrons. So a high state is actually a low energy state for holes, because you need to go from your Fermi energy to this point. So the low-lying state for germanium is actually a heavy Hall state. And if you look at the G-tensor, it actually has already a form which looks almost what we want to have. We have a heavy Hall contribution, which has a very large contribution in the Z direction and a small contributions in the plane. So the only thing is missing, this is not controllable. This is given by material properties. You don't want to change in situ your material to actually operate your qubit. However, if you confine and you have spin-orbit interaction, you get correction terms. And these correction terms are especially strong in the in-plane components. So you have here these 4 terms. You also have smaller terms here on the side, if you have a nice material. And then we already get our block form. Especially for circular dots and without strain, actually these off-diagonal terms itself directly are 0, and these here are the opposite. And this means we actually have something which can compensate for this 3q and minus 3q contribution. We have modeled this, and what you can see here is depending on X confinement and Y confinement. So I have a dot in the plane, and I try to squeeze it in the X direction or in the Y direction. So this gives me the confinement width. And what I can find that actually the effective G factor becomes 0 if I make both of these radius quite small. And this is a point which is quite interesting here, because this is effectively the point where you don't have a splitting despite a magnetic field. So you basically turn off the magnetic field, the qubit fields or the spin fields. And then if we wiggle around that point, because we can even confine more or less, we actually get directly our qubit. And these are the expressions, if you do perturbation theory, you can find out that you have some prefactors, but it's directly set by the in-plane harmonic confinement length. So if you squeeze them, squish them together, you can actually achieve that. I don't think I need to talk much about the single qubit operations, but the first requirement is, okay, we have a new qubit. Can we actually do more than only single qubit? Because if you only have single qubit operations, not enough. So how can we actually do our 2-qubit operations? The idea is simple. It's a 3-step. So you have this gapless position, a circular well separated. You either use some gates on the side to actually control it. And then you squish them in one direction. You open the gap. And when you open the gap, you can actually move them forward together. The idea why you should open the gap is because in this way you can actually imitate a Zeeman field difference, which gives you access to a adiabatic 2-qubit gate, which is easier to calibrate than swap oscillations. The second is to actually ease your constraint, because I think you can think it's quite hard to actually move them and maintaining this gapless position all the time. Might be, the good thing is it's actually not necessary. It actually helps if you don't do that when you move them. And then you bring them together, you let them interact, like the exchange interaction, and then you bring them everything in reverse. And the nice thing, this is actually very similar to what people have already showed in this paper, Utah, where you actually shuttle two particles together, let them interact with each other and shuttle them back. So it's using a very similar idea. And this gives you access to 2-qubit operations. Can you now imagine how you do readout? Because readout with degenerate qubits is a very challenging concept. There's a very big field working exactly on this. But here we want to actually read them out very quickly. And we use exactly the same principle. We go in the gapless, start in the gapless position. We squeeze them. We move them towards, but instead of doing a 2-qubit gate, we start to detune them. If they tunnel, we actually see a spin. If they tunnel, we see that our state has a certain spin configuration. And this is caused by the Pauli spin blockade. Two particles in the detuned state only tunnel if you only have a single orbital, if their states are actually anti-parallel. Or in other words, if the ground state total wave function is a singlet. If this is not the case, they will not tunnel. And this transfers a spin signal to a charge signal, which you can actually measure by different means. So actually the initialization and measurement works exactly the same way as the 2-qubit gate. Now, you can build from this now a full quantum computer. Of course, as a theorist, I can just use PowerPoint tricks to make it nice looking. The challenge is to experimentally realize that. I will talk about later. But you can maybe visualize it in such a way. You have these positions of idle points where your qubit just doesn't do anything, doesn't pick up a phase. You can just let it sit there and nothing happens. And then you have these positions where here you do X gate and here a Y gate. And maybe between these two, you want to do a XX, a 2-qubit gate. Very important, and I haven't mentioned that before, is when you do the 2-qubit gate, you actually, depending on how you squeeze them, you do a different type of 2-qubit gate. So the first squishing, the first gap you introduce fixes the axis. And then if you bring them together, you can actually get a very versatile set. And this is why you have here access to X and to Y gates. So this gives you actually new opportunities. If you think about your squeezing angle, if you basically, if you characterize it by two angles, what you can actually see is two different angles, so basically how you rotate it. And then you can find out that at different points, using one readout protocol, you really get good fidelities, and in other ones, not. But what I haven't shown you is that here you can actually read other state. So not only having access, for example, to a ZZ readout, but you can also fix it that you have a XX or a YY readout. So you can imagine that in this way, you have a very versatile easy way to do readout and this, to set apart gates from the readout process itself. And the same thing you can also do with the 2-qubit gates. What I plot here is the fidelity of an adiabatic ZZ gate, or in this case, a XX, if I use the nomenclature from earlier. But you see that it's very good at this point and here, but there is some kind of very red bad region. This red bad region is actually the regime where you, instead of getting a adiabatic gate, you actually get an I-swap gate. And from quantum error correction, we know that having access to CNOT-like gates and I-swap gates helps you in reducing the compilation length of your codes. So you have new opportunities. Of course, there are also new problems arising. And the first problem you might think of is decoherence. I have now no gap. Unlike my runner qubits, this one is not protected. It's as sensitive to noise as a normal physical spin qubit. So how bad will it be? The good answer is it will be not too much bad. The bad answer is it will be worse. And how much worse depends on the system, but it can be twice as bad in this case. So you have twice as fast decoherence, but at the opposite, you have also access to faster operations. So I would say if you use dynamical decoupling, you can actually get, because you can have here access to very fast gate times. We estimated in the order of hundreds of megahertz single qubit gate times, meaning you can filter out a lot of the low frequency noise. However, you don't want to be too many of them, because we also want to compile and efficiently compute later them. The second question is, what if I don't get the 0 point? Getting exactly 0 energy gap, I would say, is a very hard problem, because you need to measure very long to actually confirm that you are at the 0 point. So you want to avoid it. So what is the problem with that? Of course, if you have finite frequency splitting and not exactly 0, all these things, what I told you, don't work exactly like that. The good thing is if you can maintain a frequency splitting which is only on the on the order or less than what you want to do with your single qubit operations, you can actually work with that. And the good thing is you can use composite pulse sequences. Composite pulse sequences, there are sequences which basically make a better version of a gate, of a rotation gate especially. In this case, we use the quarks sequence, S quarks and the normal quarks. I will not pronounce what it is. You can find the literature online. But how they implement it is very simple, is you do first a positive pulse until some magic angle, which is the arctangents of some weird ratio. But then you do a negative pulse, and then you do another positive. So first you overshoot, then you really go in the opposite direction, very strongly undershoot, and then overshoot. And if you time that angles correctly, you get the very, very strongly suppressed error from finite qubit splitting. And you can see here directly on the plot here is if you have on the same order, you still get something the order of 10 to minus 2, 99, which might be not okay. But if it's only one order, you can actually get a 7 orders of magnitude suppression of your finite qubit splitting. So if you combine that, you can actually And the good thing is it's only 3 pulses, so it's not a very long sequence. So with this in mind, as a theorist, now the fun part actually starts, and this is to design architecture. So a very naive way to do an architecture like this is just use the kind of the dense way, have a large grid of quantum dots with surrounding barrier gates, and add your holes into it. Do a bit of distribute your sensors so you can read out everything, but more or less. Another way, and which might be actually more appealing, is to actually don't fill in or don't occupy everything. Just add a little bit of sparsity. In this way, you can actually suppress crosstalk by orders of magnitude if you don't bring them. And in this way, you would, for example, do a 2-qubit gate between these red marked regions. Then you shift them around, and then you do here another 2-qubit round. In this way, you can, very similar to what cold atoms can do, you can actually switch them around. Or you can actually take the same gates here and just connect. You don't only need to connect one shuttling line, but you connect many. You can connect more than one shuttling line to it, and then you can actually bring in qubits from a further side to that, or move them around and play with them. So that's most of my talk. So the take-home message is scaling is challenging still. You hear a lot of in media that they get bigger and bigger, but we're doing good. But we're now really hitting the limits. Wiring, heating, and crosstalk must be considered if you want to scale, because very easily physics problems can be solved and engineering problems can arise when the full concept can break down and not be realized. Hopefully simpler qubit control helps. So if we ease the control part, electronics can hopefully also be simplified, allowing for better integration. A baseband single spin qubit can be realized if you use, for example, germanium or any similar materials. And architecture designing can now start. And I want to thank all my group members and my collaborators for that.
Then we have time for questions, and I will just go around the mic to whoever has a question. Yes.
Thanks for the talk. I was wondering, you also mentioned the variability between qubits as a problem. Is that also less of a problem with this kind of scheme, or not so much?
In one sense, no. You can answer this question actually in 2 ways. The first is by designing all your qubits to be gapless, they are becoming identical by design or by construction. So you actually take that out. However, to get to this gapless regime might still suffer from a variability. And here definitely better materials help to ease it. I looked into this problem, so for especially strain, which is local and can be quite strong, actually gives a counter. You need to compensate for these local ones. So it's possible, but it needs to be seen in practice how efficient and how fast this can actually be done. And I think here, especially the machine learning from Eliška might actually do that a bit faster than.
Good. Other questions? Yes.
Thank you for the very nice talk. It seems like one of the big emphasis is that this is much better for computation, and then the other qubit schemes might be better for storage because the coherence time is better.
Mhm.
Is there ways that you can think of integrating these kinds of architectures to previous like spin qubit designs where you go into the gapless regime for computation and you go to the other regimes for like storage and kind of like shuttle between?
That's a very interesting concept, and I think it's definitely possible. We're thinking actually by moving them around, we actually know that motion narrowing actually gives us some longer coherence times. By only going into the other regime, we only get a factor of 2, which might be not sufficient. But the idea is to use dynamic decoupling sequences to store it, or even maybe connect it to other types of qubits, especially nuclear spins, which might be lying around for storage information. Yeah.
Okay, any more questions? I see there's a raised hand online. Maybe if online, can you write the question? Then that's maybe easier, because then I don't know how the... you can unmute, okay. So Monica? Maybe it doesn't work. Yes, okay, then let's take one more from the audience. If there's more questions. Yes.
So this one is maybe more about the inspiration that you've introduced to the old paper. I'm kind of curious if either they or you have a vision what kind of this ferromagnetic, if you were to go even more into this analogy, ferromagnetic ion or whatever that gives you this twist of axis, like what could it be?
Thanks. I think I can only give a wrong answer there. I think also David, one of the authors, was online earlier, or is still online. There's not much mentioned. They see it's appealing. I think the ferromagnetic textures become now more envisioned. But how exactly it can be realized, that's beyond my knowledge.
Mm-hmm. Fair enough.
Good. I think maybe one last question. Yes.
I'm almost hesitating to ask because this is a little bit like more on a speculative side, but you mentioned the optimization first. Do you think that in this kind of proposal, it's like fundamentally, are there some like fundamental difference compared to like, you know, like a normal silicon qubits from like an optimization point of view? Is your parameter number going to scale a little bit differently maybe? Anything like that? Or is it, are we just looking at the same problem like computationally?
Yeah, so the number of lines and controls can be maybe easier set because everything is electrically. You don't need these microwave signals, but the number of parameters is similar. I would not say exactly the same because they can be slightly different. I think here you have a bit more opportunities you can play, meaning you get more parameters you can optimize. But I think a rough estimation should be the same numbers. Yeah, the hope is that once you reach this regime, that you have uniform signals on top. And I think that's the main difference, because everything you make identical by calibrating it in this way. Thanks.
Okay, great. Then let's thank Max one more time.